Imagine a world where vectors could have multiple personalities. But wait, they can't. Let me show you the mind-blowing proof that explains the reason why. I'm excited to introduce this new playlist covering the appendix of this book, as linear algebra is a fundamental topic in the scientific community. If this interests you, be sure to hit the subscribe button for more. And don't forget, the full PDF of these will be available on Patreon. But with that, let's get into this proof. So the statement here of contention for the personalities of vectors comes from problem A.3. This is asking us to prove that the components of a vector with respect to a given basis are unique. Some definitions that'll help us along the way. 1. A basis is defined as a set of linearly independent vectors that span the space. So in 3 dimensions, think about the x, y, and z directions known as the I, j, and k hats respectively. I, j, and k span the 3-dimensional space, but also can arise to every other vector in the space. But I, j, k hats are all independent of one another. And we'll get into more of what that exactly means here later. Now, to be linearly independent, well, this tells us that we cannot be written as a linear combination. For example, I cannot write k hat as a linear combination of I hat and j hat. But if I were a vector in the xy plane, I would be dependent on the I hat or j hat respectively. But seeing as how bases need to be independent, we can't have any overlap like that, and that will come back to us at some point. So now that we know what the landscape is, let's actually get started in this proof because it's pretty simple but definitely telling. Alright, so for the proof, let V be a vector space with some defined bases. Whether you want to call them vector 1, vector 2, vector, or whatever amount of vectors, or equivalently, a lot of authors use this EI or E1, E2, E3 to represent the bases because it's ambiguous and you can use it for things like rectangular coordinates, cylindrical coordinates, or whatever other type of coordinates. We've seen in the quantum mechanics book, spherical coordinates used quite a bit. So that tells us quite a bit there. So keep in mind 2 different notations here, but both represent the same thing. So if we define that we have our vector space built on this basis B, then we could suppose that a vector alpha that lives in the space has 2 representation in terms of these bases, meaning that we have alpha equals A1 with some basis E1 and component A2 with some basis E2 all the way to AN EN. Now again, we're supposing that this exists. We're not saying that it does. But in the case that we let it exist, we'll show what happens. Then we also say, well, if I have an equal representation of the same thing, i.e. I'm calling the same vector alpha, but I relabel my components B1, B2, B3, and so on, then what I have to do is for AI and BI, which are the components, where they're scalars, whether they're real numbers or complex numbers, doesn't matter, but they're scalars. We need to prove that AI equals BI for all components I in the enumeration N. Okay, and so what this is telling us is that for these 2 things to actually be equal, we have to show that the components must be equal, and that's what we'll do next. Okay, so moving on, how we do this is by subtracting the 2 equations. Okay, so we take the orange alpha and the green alpha and then take the difference. So if we just put them in our brackets, we see that we have a minus sign here, and this tells us that we need to distribute this minus sign. Since we know we're in the vector space, we have all the distributivity laws that we need, all the addition laws that we need, so on and so forth. So we're good to go in distributing this to every component. Once we distribute it to every component, we know that in vector notation, just like we saw in polynomials, that we have to add them component-wise. So this E1 and this E1 need to be added together, but we have a negative B1 and a positive A1. So adding them up component-wise, we see that we get A1 minus B1 for E1, A2 minus B2 for E2, and then AN minus BN for EN. Pretty straightforward there. But what we notice is that because alpha minus alpha, if they're the same vector, that has to equal the 0 vector. So what this statement now says is that the zero vector, which again is not zero as a scalar, but has zeros for every component, this zero vector is equal to this difference here, okay? So here's where we have to make some defining statements about this zero vector equaling this difference of components. Okay, so since E1, E2, and En is a basis, this means that they are linearly independent, meaning that I can't just join together E1 and E2 into some other component, say Ej. That's not going to work because we define them as such as it is a basis. And so by this definition of linear independence, the only way for the linear combination to equal the zero vector is for all coefficients to equal 0, meaning that we have a1 minus b1 equal a2 minus b2 equal an minus bn equals 0. All of them equal 0 because it's a zero vector, and you need to compare component-wise. If that's so, what this tells us is that if a1 minus b1 equals 0, I can add the b1 over, so I get that a1 equals b1. Similarly, a2 equal b2, and then so on for an equal bn. As such, we have shown very quickly that a1 minus or ai equal bi for all I in the enumeration n, proving that the components are all unique. And the statement of uniqueness here is that, well, if I'm telling you that I'm expressing two things in a different notation, but the things are equivalent component-wise, then they're the same thing. So this tells us that we're unique by the definitions given by the bases. So a pretty quick proof, all things considered. But we have to tie in that if we see bases, we have to tie directly into linear independence, which means I can't be a linear combination. So that is beautiful like that. As such, the uniqueness is crucial because it allows us to represent any vector in the space uniquely as an n-tuple of scalars, say a1, a2, an, with respect to the given bases. This one-to-one correspondence between vectors and their coordinate representations form the foundation for many important concepts in linear algebra, including coordinate transforms and matrix representations of linear transformations, both of which we've seen heavily used in quantum mechanics. Alright, so that was a nice short video, but something that was very much needed in the whole gist of what's going on in linear algebra, because if I don't have unique representations, I could be talking about ambiguous objects. As such, if this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I'm able to keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful for each of you for believing in this journey. And if anyone else is interested in supporting the channel and joining our Patreon community, you can check out the link in the description below. Together, we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching, and until next time, stay curious.